Hello, welcome back to STEM and Society Unplugged. Today we will be diving into periodic trends and look at a preview of chemical bonding. To begin, we must understand periodic law. Periodic law states that when atoms are arranged in order of increasing atomic number, so the number of their protons, group and period patterns emerge. The group and periods on a periodic table are as follows. Groups are the columns of the tables. There's 18 groups, and the groups dictate the number of valence electrons atoms have, or at least for groups 1 to 2 and 5 to 18. And periods are the rows of the table. That's how many shells, if you will, if you're looking at that type of model, like the amount of circles that surround the nucleus. So those are groups and periods. The patterns and trends in which emerge, the main those are atomic radius, ionization energy, isoelectric, electronegativity, and electron affinity. These trends can be looked at as trends, which they are, or they can look at ways we can describe activity or properties of, or measure properties of elements and atoms and their behaviors. Atomic radius is the distance from the nucleus to the outermost electron. Ionization energy is the amount of energy needed to remove the most loosely held electron from its atom. Isoelectric is when atoms with the same number of electrons have the same number of electrons but different number of protons. These would be ions. Electronegativity is the degree into which elements are shared between atoms in a chemical bond. Electron affinity is the amount of energy released when an atom gains an electron. Now to go over these in more detail. Atomic radius is the size of an atom. Ionization energy is how much energy you need to put in to break bonds, or not break bonds, to remove the outermost electron, so the electron in its valence shell, from the atom. Isoelectric is pretty self-explanatory. Electronegativity is to whenever you are bonding elements, where the electrons are most likely to be found, or most likely what area or which element they're closely going to be towards. And electron affinity is the same, it's a little bit more self-explanatory. Now, to understand these trends on a periodic table, we have a mock periodic table here, and we have arrows. The black arrows represent how the trends of ionization energy, electron affinity, and electronegativity look on a periodic table. So the higher up a group you go, the greater ionization energy, the greater electronegativity, the greater electron affinity there is. And as you go right across a periodic table, the higher ionization energy, the higher electronegativity, and the higher electron affinity. That is totally opposite when you get to atomic radius. Atomic radius again is the size of an atom, and those are symbolized by the green, light green arrows. As you go down a group, you have higher atomic radius, and as you go left a periodic table, the greater the atomic radius is. And this is all because as you go down a group, you have more levels and you have more areas where the valence electron is, so it gets wider. Okay? And as you go left a periodic table, there's less protons, so less pull on the valence electron, so there's a lot less pulling it in, squeezing it in. Now to go into the three mentioned before, the former, ionization energy and electronegativity and electron affinity, act this way because as you go up a group or you go right a period, the atom gets smaller. And ionization energy, electronegativity, and electron affinity have all to do with the size of an atom. The smaller the electron, the higher those trends will be, the higher those measurements would be. Okay? Now, all these patterns and trends play massively into chemical bonding and drawing Lewis structures and structural formulas and bond angles. Now, a little preview of chemical bonding is seen here. And again, before we get into this, now that we have an actual illustration of the periodic table, atomic radius is larger within these blue shaded elements, which are more metallic. The more metallic or metals will always have higher atomic radius than nonmetals or metalloids. Okay? And electron affinity, electronegativity, and ionization energy will be higher in nonmetals, less metallic things, or metalloids. In matter of fact, electronegativity is highest within these elements: chlorine, fluorine, oxygen, and nitrogen. These elements here, these elements have the highest electronegativity. Okay? Now, that's just a little ender to that section. But chemical bonding, okay? Chemical bonds can come in three major sections. There's metallic bonds, there's ionic bonds, and there's covalent bonds. Sorry for the misspelling there. Metallic bonds are between two metals, or a metal and a metalloid. And metalloids are these purple shaded elements here. Ge and SB, so germanium and antimony, are the more metal-like metalloids. And a quick, the behavior of electrons in a metallic bond is that there's mobile electrons. That allows for metals to be great conductors of electricity because electrons can go wherever. Ionic bonds are between nonmetals and metals. And the metal in the behavior of electrons in these types of bonds is that the metal will lose an electron, gaining a positive charge overall, its ion being positive, and nonmetals will gain an electron, resulting in them having a negative charge. Again, sorry for the misspelling of covalent. Covalent bonds are between molecular compounds, more specifically nonmetals and nonmetals, and nonmetals and metalloids. Probably, and those metalloids are most likely going to be boron, silicon, arsenic, and Te here, the upper staircase of the 7 metalloids.